In 1899, a German physicist named Max Planck calculated the smallest length that can physically exist, 1.6 times 10^3 meters. Try to measure anything smaller and spacetime itself collapses into a black hole. There are 10 levels of scale between that point and the 93 billion light-year edge of the observable universe. You exist at exactly one of them. Here is what life looks like at every single level, including the one where life should be impossible, but isn't. The Planck length is not small the way a grain of sand is small. It is small the way nothing is small. If a single hydrogen atom were magnified to the size of the observable universe, the Planck length inside that atom would still be smaller than a grain of sand. This is where the scale journey begins. But before ascending even one level, consider what sits just above the Planck floor and why physicists lose sleep over it. At 10^3 meters, spacetime is not smooth. It foams. It churns. John Wheeler named this quantum foam in 1955, and at this scale, space itself flickers in and out of geometric coherence 30 million trillion times per second. No life exists here. No structure can. The energy required to probe one Planck length would be 1019 GeV, roughly the output of a star compressed into a single point. Even the concept of a particle breaks down. This is not a place. It is a threshold, the universe's own margin of error, written in the language of physics. Rising 10 orders of magnitude lands at the scale of quarks, 10 meters, a proton's interior. 3 quarks bind here through the strong nuclear force which behaves in reverse. The harder 2 quarks are pulled apart, the stronger the force pulling them back. Physicists call this confinement. Quarks have never been observed alone. Not once, ever, anywhere. At 10 meters, the proton itself comes into view 1 femtometer across. Inside every atom of every human body, inside every bone and blood cell and synapse firing right now, protons are doing something extraordinary. They are spinning, not metaphorically. Protons carry angular momentum, a real physical rotation, and no one fully understands where that spin comes from. Jump to 10 meters, the atomic scale. 1 angstrom. This is where electrons orbit. In 1913, Niels Bohr draws his first model of the hydrogen atom in Copenhagen, and it is wrong, but beautifully wrong. The real electron does not orbit like a planet. It exists as a probability cloud, a smear of likelihood wrapped around a nucleus it never quite touches. This is where chemistry begins. Every drug ever synthesized, every poison ever brewed, every protein ever folded, all of it happens at the angstrom scale. And yet the atom is almost entirely empty. If a proton were the size of a football stadium, the nearest electron would be orbiting 4 miles away. Matter is, in the truest sense, mostly nothing. What comes next will make that feel ordinary. Something lives at the next scale up, and it should not be able to. But that is a story for scene 28. First, the nanoscale, 10 meters, 1 nanometer. A human hair is 80,000 nanometers wide. A strand of DNA is 2 nanometers wide. At this scale, a single ribosome, 25 nanometers across, reads genetic code and assembles proteins at a rate of 200 amino acids per second, without rest, without error, inside every living cell on Earth. The nanoscale is the floor of life. Below it, chemistry. Above it, biology. The transition happens in the space of a few dozen nanometers, and it is the most consequential boundary in the known universe. In 1953, James Watson and Francis Crick hold up a wire model 1.8 meters tall to represent a molecule just 2 nanometers wide, and human medicine is never the same again. At 10 meters, 1 micron bacteria appear. Escherichia coli is 2 microns long. It has no nucleus, no organelles, no nervous system, and yet it senses chemical gradients, navigates toward food, and reverses direction in 200 milliseconds when threatened. It has been doing this for 3.5 billion years. Every human alive today is outnumbered 1.3 to 1 by the bacteria living inside their own body. One step up, 10 meters, 10 microns. Here sits the human red blood cell 8 microns across, shaped like a biconcave disc specifically to maximize surface area for oxygen exchange. It has no nucleus. It lives 120 days. In that time it completes 75,000 laps around the human circulatory system, traveling roughly 1,000 miles without a single engine, pushed entirely by the pressure of one beating heart. At 10 meters, 1/10 of a millimeter, the human egg cell appears. It is the largest cell in the human body, barely visible to the naked eye. It is 100 microns across. A sperm cell is 50 microns long, but its head, the part carrying the genetic payload, is just 5 microns. The entire instruction set for a human being fits inside a volume smaller than a grain of fine sand. Pattern interrupt. Stop. In 1665, Robert Hooke opens a slice of cork under a handmade microscope and sees tiny rooms. He calls them cells, from the Latin cella, meaning small room. He has no idea he is looking at the dead walls of dead plant cells. He has no idea that inside living versions of those rooms, machines made of protein are folding, cutting, and copying molecules with nanometer precision. He just thinks they look like little rooms. Now ascending to the human scale, 1.7 meters, the scale of a standing adult. At this level, for the first time in the entire journey, an observer can be seen with unaided eyes. But what comes next is the scale most people assume they understand, and almost nobody does. The gap between one human body and the next object on this scale is not a step. It is a cliff. Between 1 meter and 1 kilometer lies everything civilization has ever built. The Eiffel Tower, 330 meters. The Burj Khalifa, 828 meters. But here is what no architectural drawing captures. A healthy human eye on a clear night standing on flat ground can see a candle flame from 48 kilometers away. The human sensory range across scale is absurdly, almost insultingly, narrow. And what comes after the kilometer mark changes everything. At 103 meters, 1 kilometer, cities begin to take shape from above. The island of Manhattan is 21 kilometers long. Seen from 400 kilometers up, aboard the International Space Station, it is a gray sliver in a brown-green coastline. Astronaut Scott Kelly, completing his 340-day mission in March 2016, later writes that from orbit, every border drawn by humans is invisible. Only rivers and coastlines remain. Here is what the next 3 levels build toward. A discovery made in 1996 by a geologist named Philippa Uwins, inside a piece of Australian sandstone, will contradict a formal NASA ruling about the minimum size at which life is physically possible. And the things she finds are alive, growing, and reproducing. But first, the viewer needs to understand exactly how big the universe gets, so that what lives at the smallest scale feels as extraordinary as it truly is. At 107 meters, 10,000 kilometers, Earth's diameter comes into view, 12,742 kilometers. From this altitude, the planet looks blue. Not partly blue, overwhelmingly blue. Oceans cover 71% of the surface. All of human history, every war, every empire, every cathedral, every landfill, occupies 29% of one rocky sphere orbiting an unremarkable star in an outer arm of a middling galaxy. At 109 meters, 1 million kilometers, the Moon fits inside the frame. The average Earth-Moon distance is 384,400 kilometers. In 1969, Neil Armstrong and Buzz Aldrin take 3 days to cross it aboard Apollo 11, traveling at 39,000 kilometers per hour. Light crosses that same distance in 1.3 seconds. The Moon is close. Everything else in the solar system is not. At 10-11 meters, 100 million kilometers, the Sun enters the picture. Its diameter is 1.39 million kilometers. 1,300,000 Earths fit inside it. And yet, on the cosmic scale about to unfold over the next 4 levels, the Sun is so ordinary it does not merit a label. There are stars in the Milky Way 1,700 times its diameter. The star Uy-Scuti, if placed at the Sun's position, would swallow Jupiter. At 10-13 meters, 10 billion kilometers, the solar system's outer edge approaches. The Voyager 1 spacecraft, launched September 5, 1977, crosses this distance and keeps going. In August 2012, it exits the heliosphere, the bubble of solar wind surrounding the Sun, and enters interstellar space. It is moving at 61,000 kilometers per hour. The nearest star is still 440 years away at that speed. Pattern interrupt. The distance between stars is not empty. In every cubic centimeter of interstellar space, there are approximately 1 atom's worth of hydrogen. 1 per cubic centimeter. For context, the air at sea level contains 27 million trillion atoms per cubic centimeter. The void between stars is the closest thing to true nothing that nature actually produces. And life still finds a way to grow in it, on grains of interstellar dust, in molecular clouds, in forms no one expected. At 1016 meters 1 light-year, the Milky Way scale becomes visible. The galaxy is 100,000 light-years across. It contains between 100 and 400 billion stars. And here is what is coming in the final 2 levels. Structures exist that make the Milky Way look like a single cell in a human body. What is about to appear on screen is the largest confirmed structure in the universe, and it has a name. At 1021 meters, 100,000 light-years, the local group comes into view. 30-odd galaxies bound by gravity stretching across 10 million light-years. The Andromeda Galaxy, 2.537 million light-years away, is approaching the Milky Way at 110 kilometers per second. In approximately 4.5 billion years, the 2 galaxies collide, merge, and form a new elliptical galaxy astronomers have already named Milkomeda. At 1024 meters, 1 billion light-years, galaxy filaments appear. These are the largest structures in the universe, threads of dark matter and galaxy clusters woven into a cosmic web. The Hercules Corona Borealis Great Wall, discovered in 2013, stretches 10 billion light-years across. It is so large it should not exist according to standard cosmological models. It exists anyway. At 1026 meters, the Observable Universe, 93 billion light-years in diameter. Not the whole universe, just the part from which light has had time to reach Earth since the Big Bang. Beyond that edge, space continues, possibly forever. The observable universe contains an estimated 2 trillion galaxies. Every single one of them is made of the same atoms, governed by the same physics, born from the same singularity 13.8 billion years ago. Now the payoff. In 1996, geologist Philippa Uwins at the University of Queensland examines freshly fractured Australian sandstone under an electron microscope. She finds spherical structures between 20 and 150 nanometers in diameter, growing, budding, and self-replicating. They are alive. The problem: NASA's own astrobiology panel had formally ruled that no living cell can function below 200 nanometers. The smallest of Uwins' organisms measures 20 nanometers. That is 10 times smaller than officially possible. The structures Uwins finds are later named nanobes. They contain DNA. They grow on agar plates. They reproduce. Independent researchers confirm the findings, and they are found not in some exotic laboratory environment but in ordinary rock from 3 to 5 kilometers underground, in conditions of pressure and temperature that should sterilize everything. Life, it turns out, did not read the NASA ruling. So here is the answer to the question opened at the very beginning of this journey. The scale level where life should be physically impossible, but isn't, is the nanoscale, 20 nanometers, 10 times below the threshold science declared uncrossable. From the Planck foam at 10.3 meters to the 2 trillion galaxy web at 10.26 meters, life appears precisely where physics says it cannot. The question worth leaving in the comments: what else is alive in the places we haven't looked yet?